Okay, in today's lecture, we're going to talk about gases. So some general properties of gases. They take the volume and shape of their container. They consist of small particles that move randomly at high velocity. The attractive forces between those gas particles are very small. Also, the actual volume occupied by particles is very small compared to the volume the gas takes. The particles are constantly in motion, and the average kinetic energy is proportional to the temperature in Kelvin. Okay, let's talk about a couple different properties of gases in more detail. So first we're going to talk about pressure. So when gas molecules hit the wall of a container, they exert pressure. Atmospheric pressure is the pressure air molecules exert on us. The higher altitude, lower pressure. And usually the units of pressure are atmospheres and millimeters of mercury. That's what we usually deal with. And you could think of, if you're in a room, we're all in a room together, closed walls. If we're walking around, we're going to hit each other and the walls periodically. That's analogous to gas pressure. The next property is volume. So the volume the volume of a gas is equal to the volume of the container it's in. Usually the units are liters or milliliters. So if you have, again, let's think of a room, you have all the gas in a room, you can cut the room size in half and still fit all of that gas in that new room, right? And the gas just takes the volume of that container. Then temperature, so like I said in the first slide, temperature is related to the kinetic energy of gas particles. So if you double the temperature in Kelvin, you double the kinetic energy. And this in Kelvin is really important whenever we do gas calculations and gas laws, which we're going to look at in a couple minutes, or in a couple slides. You need to make sure your temperature is in Kelvin. It can't be in Celsius or your calculations won't work out. Then finally, the amount of gas. We talk about the amount of gas in moles, or N, and that's just the quantity of gas present. We usually measure the amount of gas in grams, in grams, but we have to convert it to moles for calculations. Okay, let's talk about the ideal gas law. So the ideal gas law is Pivnert. You'll hear people say that. It's P times V equals nRT. So P is pressure of the gas in atmospheres. V is the volume of gas in liters. N are the number of moles of gas. T is the temperature in Kelvin. And R is a gas constant. It's 0.08206. And the units are liters times atmospheres over moles times Kelvin. Down here under pressure, I have conversions for you. So these are, if you ever are given a pressure in millimeters of mercury or torr, again, you'll have to convert it to atmospheres. But 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torrs. So if you know 3 of the 4 variables for gas, you can calculate the 4th. For example, if I know pressure, volume, and number of moles, I can calculate the temperature of the gas. If I know volume, number of moles, and temperature, I can calculate the pressure. If I know pressure, number of moles, and temperature, I can calculate the volume. If I know pressure, volume, and temperature, I can calculate the number of moles, so on and so forth. So let's look at just one example here. So what is the pressure of 0.75 moles of a gas that occupies a volume of 1.25 liters at a temperature of 298 K? Well, we're going to use the ideal gas law. The first thing we want to do is rearrange so we have pressure by itself. That's what we're calculating, right? So we can divide both sides of the gas law by V, and we get pressure is equal to number of moles times the gas constant times temperature divided by volume. Remember, N has to be in moles, we're good there. T has to be in Kelvin, we're good there, and volume has to be in liters, we're also good there. So then we just plug it in. So we have 0.75 moles times 0.08206, the gas constant, times 298 Kelvin divided by 1.25 liters, and we get a pressure of 15 atmospheres. We have 2 significant figures because our number of moles has 2 significant figures, which is the lowest number of sig figs. Okay, so what if I have a gas though and I change something? How do I calculate that effect? We can use the combined gas law, which says that P1 times V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. So what I mean by this is, let's say we have a gas and I know the pressure, I know the volume of my gas, I know my number of moles, I know my temperature, and I change the volume, right? And I want to know how that affects the pressure. How does my pressure change? So generally speaking, when we're working with the combined gas law, we have two things that are going to stay the same. So maybe number of moles and temperature. We're going to change one thing, and we're going to calculate how it changes the other thing. So, we might, like I said, we might know number of moles and temperature. Those are staying the same in both scenarios. So N1 and N2 are the same, T1 and T2 are the same. I know my initial pressure and volume. Let's say I change my volume. I can calculate that, which is V2, my new volume. I can calculate P2, which is the new pressure. Or if, let's say, number of moles and volume are staying the same. So N1 and N2 are the same, V1 and V2 are the same. And I know my pressure and temperature of my gas, and then I decide to change the temperature. I can calculate the new pressure. Or if I decide to change the pressure, I can calculate the new temperature, so on and so forth. So when you're given a problem with this, what you need to do is figure out, okay, what two things are staying the same in both scenarios, and then what's changing. So let's look at Boyle's law, which is the relationship between volume and pressure. So if you can see here, we have this system with a piston and a movable piston. And in my first scenario, I have a volume of 4 liters and a pressure of 1 atmosphere. Well, I can move the piston and change the volume. How does that change the pressure? You can see here, if I have the volume, my pressure doubles, which means pressure and volume are inversely proportional. So if I raise one, I lower the other. So if we look at our combined gas law then, in this scenario, N and T are staying the same. So if we're doing calculations, we'll use this equation, P1 V1 equals P2 V2. So again, you can just get rid of the variables that are not changing between our two scenarios. In this scenario, our temperature is staying the same and our number of moles are staying the same. So Boyle's law explains inhalation and exhalation, actually. So when we inhale, our diaphragm contracts and moves down. This increases the volume in our lungs, which decreases the pressure in our lungs compared to the atmosphere. The pressure in our lungs is lower than atmospheric pressure, which causes air to rush into our lungs. Then when we exhale, our diaphragm relaxes, it moves up, which decreases the volume in our lungs, which increases the pressure in our lungs. And now the pressure in our lungs is greater than atmospheric pressure, so that causes air to rush out. So let's look at a practice problem. So let's say we have an air in a 5-liter tank. It has a pressure of 1.2 atmospheres. What's the pressure when the air is placed into the following tanks? 1 liter and 2,500 liters. So let's think about this for a second, okay? So we have air in a 5-liter tank. Well, let's just take the first example. So we have a 5-liter tank, pressure of 1.20 atmospheres. If I change the volume to 1 liter, I'm lowering the volume. And remember, pressure and volume have an inversely proportional relationship. So if I lower the volume, I'd expect my new pressure to be higher. So again, we're going to use P1 V1 equals P2 V2, and we just plug and chug. So my initial pressure is 1.20 atmospheres. My initial volume is 5 liters. I'm calculating my final pressure, and my new volume is 1 liter. Divide both sides by 1 liter, and I get, that should say 6 atmospheres, not 6 liters. I apologize. So now you should try the second one. So same scenario, but what happens if I change the volume to 2,500 liters? And again, think about it. If I start at 5 liters and I increase the volume to 2,500 liters, since they have an inversely proportional relationship, I would expect my pressure to decrease. So try it out. Okay, now let's talk about Charles's law. And Charles's law deals with temperature and volume when my pressure and number of moles stays constant. So you look at this scenario, I have something with a movable piston again, and I'm going to change the temperature. So my number of moles, and I'm going to keep my number of moles and keep my pressure constant. So you can see here, In my first scenario, I have 1 liter, my volume is 1 liter, and I have temperature of 200 Kelvin. And if I increase the temperature to 400 Kelvin, that's going to increase my volume to 2 liters. So that means temperature and volume are directly proportional. I increase one, I'm increasing the other. So since N and P are staying the same, we can use the equation V1 over T1 equals V2 over T2. Let's look at another practice problem. So we have a sample of neon. It has an initial volume of 2.50 liters at 127 Kelvin. What final temperature is needed to change the volume of the gas to the following? So let's look at the first scenario. So we have an initial volume of 2.50 liters, and we have final volume of 7.50 liters, which means I increase my volume. Since since temperature and volume are directly proportional, I'd expect if my volume increases, my temperature increases. So let's look. So we're going to use V1 over T1 equals V2 over T2. Plug in, my initial volume is 2.50 liters. My initial temperature is 127 Kelvin. My final volume 7.0 liters. We're going to solve for T2. So we multiply both sides by T2, multiply both sides by 127, and then divide both sides by 250. Or just cross multiply, divide. Just do some algebra to rearrange to solve for T2. And we get 381 Kelvin, which is what we expect. We increased our volume, so our temperature increased. So you should try the next one. So what happens? I'm again increasing my volume, so we would again expect our temperature to increase, but go ahead and try it out for yourself. And again, like I said before, but I just want to reiterate, your temperature has to be in Kelvin. If it's not in Kelvin, it's not going to work. Try it out for yourself. Do these calculations with the temperature in Kelvin, and then do the calculations with the temperature in Celsius. You will get different answers. Okay, let's look at the next law, Gay-Lussac's law, which it talks about the relationship between temperature and pressure. So previously we were talking about temperature and volume. So this says if I keep my number of moles the same and I keep my volume the same, but I increase the temperature, I'm going to increase the pressure. This makes sense, right? We talked about how temperature is directly related to the kinetic energy of gas particles, and the kinetic energy, remember, is energy of movement. So let's say we're all in a room together again, same number of people, same room size, and we start moving, we're walking around. We're going to hit each other. And again, remember how I said as we're hitting each other and hitting the walls, that's analogous to pressure. Well, if I increase our kinetic energy, increase our temperature, we're going to start moving faster, right? And we're going to hit each other more and hit the walls more. So we're increasing our pressure. So since our pressure and temperature is changing, that means our volume and number of moles is not changing. So our new equation is P1 over T1 equals P2 over T2. Okay, so let's look at an example. So we're going to calculate the final pressure if a gas with an initial pressure of 1.25 atmospheres and temperature of 273 Kelvin is cooled to the following temperatures. So if I'm cooling, so I'm lowering the temperature, that means my pressure should be lower, right? Because temperature and pressure are directly proportional. So we'll look at the first one. So again, we want to use P1 over T1 equals P2 over T2. And just plug in. We have 1.25 atmospheres over 273 Kelvin equals P2 over 125 Kelvin. Multiply both sides by 125 Kelvin. And we get a new pressure of 0.572 atmospheres. So it's a lower pressure, which is exactly what we expected since we lowered the temperature. So you should try the next problem. And again, I don't know what happened, sorry. Again, the temperature has to be in Kelvin. Okay, let's look at Avogadro's law. See if I can fix. There we go. So now we're going to look at Avogadro's law, final law, and that's a relationship between number of moles and volume. So Avogadro's law says if I change my number of moles of gas, but I keep my pressure and temperature constant, my volume is going to change. And as you can see here, so in the first example, I have 1 mole of gas, 1 liter volume. If I change the number of moles to 2 moles, my volume increases to 2. So these are, again, directly proportional. So if I increase my number of moles, I increase my volume. So the equation we'll use is V1 over N1 equals V2 over N2. So let's look at a practice. A weather balloon with a volume of 52 liters has 2 moles of gas in it. What is its volume when you add the following amounts of gas to the balloon? So we expect, right, if we're adding gas, we're increasing the number of moles, so our volume should increase too. One thing to note when you read these problems, make sure you read them carefully. The question says, what is its volume when you add the following amounts of gas to the balloon? Not when you have these final amounts of gas in the balloon, which means our final number of moles is going to be 2 plus the amount we add, so 3 or 1.5. So let's look at an example. We use V1 over N1 equals V2 over T2. My initial volume is 52 liters. My initial number of moles is 2. We're going to calculate our new volume, and we have 5 moles for N2. Again, because we started with 2 moles, and we added 3, so now we have 5 moles. Solve for V2, and we get 130 liters, which is what we expect. We expect our volume to be bigger. So again, you should try the next one. Okay, now we're going to talk about Dalton's law. So Dalton's law said that in a mixture of gases, the total pressure is equal to the sum of the pressures of each individual gas. So if we have P total, that's equal to P1 plus P2 plus P3, so on and so forth. So you can think about this, for example, in the air. The air is a mixture of gases, right? It's got oxygen and nitrogen and carbon dioxide and a couple other things. Well, we know the pressure of the air, but each individual gas type has its own pressure too. So let's look at a calculation. So a typical sample of air in the lungs contains O2 at 100 millimeters of mercury, N2 at 573 millimeters of mercury, carbon dioxide at 40 millimeters of mercury, and water vapor at 47 millimeters of mercury. What's the pressure of air in the lungs? Well, again, we know our total pressure is equal to the sum of all of our partial pressures of gases. So our total pressure is 100 millimeters of mercury, which is the pressure of oxygen, plus 573 millimeters of mercury, which is the pressure of nitrogen, plus 40 millimeters of mercury, which is the pressure of water vapor, plus 47 millimeters of mercury, 40 was the pressure of CO2, 47 is the pressure of water vapor, so our total pressure is 760 millimeters of mercury, which is atmospheric pressure. Also, if you know the total pressure and you know the partial pressures of all but one of your gases, you can calculate that partial pressure.